Okay. Well, missed all the Diels-Alder stuff, so might be. All right, let's move on to these electrocyclic reactions, okay? Again, I'm gonna give you this molecule, this conjugated diene in the straight chain format, and you're gonna have to rotate it into that S-cis conformation. And again, we're gonna do electrocyclic reactions.
This reaction is the one where it closes.
Exactly. Yeah. So just to kind of keep these electrocyclic reactions straight, the Diels-Alder are when you have two substrates leading to one cyclic product. The electrocyclic is when you have one substrate and you basically have like a ring closing reaction.
It's an intramolecular reaction.
It is an intramolecular reaction, absolutely. But the first step is I got to get these double bonds to where they're like in kissing distance, basically. Okay. Okay. So again, you sort of have to have an idea of what it is that you want your final shape to look like. And I know that I have, really, I'm going to, again, focus on just this conjugated diene piece, the 1, 2, 3, 4. And so I want these to be arranged in this S-cis format here. Okay. Now I'm going to have to decorate with these chlorines, 1, 2, 3, 4. And what am I going to make sure I do to put them on there correctly?
Cis to cis, trans to trans.
Yeah, I'm just going to look at the stereochemistry of the double bonds. So this one here should be what? Cis or trans?
This. Oh, no.
Cis. So I'm just going to, when I draw that chlorine in, I'm going to make sure it's cis. And the other one is trans.
Oh.
So when I draw that in, I'm going to make sure it's trans. Okay, so everybody give me the two products that you would get first if you reacted this molecule with heat, and then if you reacted it with light.
For the exam, sorry, my internet keeps doing these like 2-second drops where it'll be like lost connection to Canvas. Is that going to screw up my exam or for the exam? Do you know?
I
only
don't,
asked.
but if it does, we can cross that bridge when we come to it.
Okay, I only asked.
I honestly had anticipated that, and so if that is, because I know I have a few y'all that live in the mountains. If that is a problem, I have a backup plan, but we'll figure that. If that happens, we'll address that.
Okay, I only asked because it did it just now, so it was just reminded me.
It could possibly, because I've had one time my laptop died in the middle of an exam and a deal. And
Certainly, if it dies, then you would have technically logged off of campus, and that'll be another thing we'll have to address. But for the vast majority of people, I don't think it'll be an issue. But if it is an issue and come the exam, let me know and we can figure something out. Okay, so obviously this has got this heat and light arrow because we get different products, whether this reaction happens in the presence of heat or in the presence of light. I guess first, like what is my product going to look like in both cases? I'm going to form this what?
A 4-membered ring.
Absolutely, right? So I have 1, 2, 3, 4 carbons. So my electrocyclic product will be a 4-membered ring in all cases. Similar to the Diels-Alder, you're going to have a new double bond formed between what was your existing double bonds in your old compound. So this between carbons now, I guess let me just number carbons. 1, 2, 3, 4. 1, 2, 3, 4. So notice that I have this new double bond between carbons 2 and 3. The question though, the hard part of this is going to be the orientation of these other groups, right? And you know, in the lecture video, you saw that there's this big convoluted explanation regarding the HOMO and the LUMO and how these things are going to rotate, conrotary versus disrotary, all that good stuff. But we actually simplified that into a sort of simplified set of rules where we're looking at the stereochemistry of the reactant. We could pick the stereochemistry of the product. And what I did was kind of made up my own stereochemistry for these dienes, where we looked at how these two groups are oriented relative to one another. By that, I mean up here on carbon 1, my chlorine is pointed down. Likewise, on carbon 4, my chlorine is pointed down. So since they're both pointed in the same direction, we said that this was cis-like.
I think that's where I was confused because I don't know what you meant by cis-like and
Meaning that
trans-like.
so whether or not, so let me just draw the other trans-like version, would be if one of them was pointed up and the other one was pointed down, that would be trans-like. And I mean, it's a completely made up thing. I'm just trying to simplify things for the sake of the problem. So you're totally forgiven for not knowing what the heck cis-like is, because I just made it up. But point being is, if we can see this cis-like stereochemistry or trans-like stereochemistry of our reactants, we can easily figure out what the products are going to be. Okay, so take a second to convince yourself that this is indeed cis-like and this is indeed trans-like, given the orientation of those substituents. Cis-like again means they're pointed in the same direction, either both up or both down. Trans-like meaning they're pointed in different directions. Okay, and then on the lecture slides, oh, hold on. Okay, so we're doing a 4-membered ring, so let's just focus on this. Is this compound here going to be, everybody just take a second, do it on your own. Tell me if this is going to be cis-like or trans-like.
Trans-like.
Cynthia, can you see it? For this guy?
Yes.
Yes, awesome.
They're
Right,
both
so this will be
Trans.
trans-like because this one's pointed up and this one's pointed down. They're pointed in different directions.
Gotcha. I
Okay.
think I was trying to look at them like at each double bond separately and be like, is this or trans?
Yeah, no, I hear you. And it's a little bit different than that. But
Gotcha.
and so what we can see is that in the presence of heat, we would get the trans product, and in the presence of light, we get the cis product. So what we did is we sort of simplified things, saying if we start with trans-like, in heat, we get trans, and in light, we get cis. So this is this little table that I made. If you have 4 electrons, under heat, there will be no change, meaning if you start with trans-like, you'll get the trans product. But in the presence of light or the photochemical reaction, there will be an inversion, meaning cis will go to trans or trans will go to cis. Notice that it's different for if we started out with the 6 electron version of these types of reactions. In the presence of heat, there's an inversion, and in the presence of light, there's no inversion. Okay?
So we know this shortcut, but on the exam for like multiple choice, will we have to know con-rotary, dis-rotary, and have like remember what that means? Or can we just rely on
I'm
the
making an
shortcut?
executive decision that those vocabulary words aren't going to be on the ACS exam. So we're going to simplify things. Fingers crossed that that's true. But yeah, I really think that that will be the case. And so that's why I've created this simplified system. Okay, and then this might seem like a lot to memorize, but if you notice the pattern, right, this is the same as this. You only really have to remember one of them. Like 4 pi electrons under thermal is no change. That should help you fill in the rest of this table, just given the sort of checkered pattern that it is. So just in terms of, I know memorization's a pain in the butt. So then let's apply this to our example here. We started out with a cis-like compound. So what are we expected to get in the presence of light? An inversion or no inversion?
Inversion.
Right, so in the presence of light, we would expect to have an inversion for 4 pi electrons. So that means we would go from cis-like to trans-like, or to trans. And I'm going to be lazy and do plus enantiomer. And that means in the presence of heat, we have no inversion. So our cis-like will remain cis.
I have a question.
That is a good one, Theo. What's up, Andres?
Okay, so Gina, you know how you went over that if it's a 4 electron, it would be so with light. If it's cis, it would be trans, or
Yeah, and if it's trans, it would be cis. There's going to be an inversion of the stereochemistry.
It flips.
The
It
inversion
flips.
is the important part to remember.
Yeah. So
Oh,
if we wanted to do the other example, I'm sort of getting real messy running out of room here, but let's just see if we can squeeze it in here. If instead we started out with the trans-like and we had heat, we would again we expect there to be no change, so trans-like would lead to the trans product.
okay, and so for light, they'll be pointing the same direction.
Correct.
Okay.
It would be the inversion. Right, here was the inversion. Here was no change.
Oh, okay. So, and if it were to be on a 6 electron, so it'll just be the inversion of it, right?
Well, if it's going to be a 6, so this is what this table is telling us. For 6 electrons, if it's heat or thermal, you would expect there to be the inversion. For 6 electrons, if it's light, you would expect no change.
Oh, okay.
All right, so this is kind of the master cheat sheet table for the electrocyclic reactions.
Okay. What slide is that? Is that slide 16?
Yep, 1675. It's gonna, if you download the lecture slides, it's gonna be blank, and I filled it in on the video.
Okay.
I might have actually filled it in when I posted the lecture slides. I don't remember. But
It's blank. You just gotta write it.
boom. So yeah. Cool. All right. So I'm pretty sure we've passed that hour mark. I got a few more problems that I was going to go through. This took a little bit longer. At this point, I've got everybody on attendance. You guys have stayed for an hour. So if you're done, you can be done. I'm going to go through a few more examples. So if you guys want to hang around and study a little bit more or have any questions to ask, that's perfectly cool as well. All right. The next one I wanted to do is a Sigmatropic reaction. And again, just to be a huge pain in the ass, I want to make sure that everybody knows how to rotate these molecules into the correct conformation. All right, so I'm going to give you this as a linear chain, and you're going to have to rotate this into what?
Cis, like the S cis.
It would be S-cis if they were, these double bonds were 2 apart, but it's actually a little bit different for the sigmatropic. Remember, sigmatropic reactions happen when your double bonds are perfectly spaced 1,5. And so you're going to need to kink this into basically a hexagon shape.
Well, for both of them, well, I mean, the double bonds are going to be on the ends for both of them, so you can just kind of draw the hexagon and slap the double bonds on.
It's not, you're right, Bryce. It's not too bad, but it's still the rotating molecules, I've realized, is something that's tough for people. So yeah, you just want to make sure that you, when you draw this in the kinked conformation, you didn't draw a completely new molecule. right, so let me show you how I would do this real quick. Again, I have these 6 carbons that I want arranged in a ring. So the first thing I'm going to do is sort of draw a hexagon, but not draw in the bonds yet. I want to make sure everything's connected correctly. That's the hard part. So I'm going to go through and just number 1, 2, 3, 4, 5, 6. And then I'm going to draw in all the bonds between, like, who should be bonded to who here. In this case, 1 should be bonded to 2, 2 should be bonded to 3, 3 to 4, 4 to 5, 5 to 6. But 1 and 6 should not be bonded. Right? Notice up here, 1 and 6 are not bonded. Now I got to make sure my double bonds are in the correct place. Where should my double bonds be? Between carbons what and what?
1 and 2 and 5 and 6.
Yeah, between carbons 1 and 2 and carbons 5 and 6. I should have double bonds. Now the only thing that I'm missing are all these methyl groups. And so I just need to make sure that my carbons that contain methyl groups on my picture above also contain methyl groups on the picture below. So that's carbon 2 needs a methyl group, carbon 3 needs a methyl group, carbon 4 needs a methyl group, and carbon 5 needs a methyl group. Okay, so just to sort of clean this up. This is this exact same molecule, but sort of kinked in the correct conformation that will have a sigmatropic reaction. Okay. Well, put this right there. Okay. Now, again, these are going to be intramolecular reactions. So you have one substrate. The difference between these and the other 2 pericyclic reactions is you're not going to form a ring. You're going to make a new sigma bond somewhere, but you're also going to break a sigma bond. That's what makes the sigmatropic reaction sigmatropic. Okay, so you're going to see that at the end, we actually don't have a cyclic compound, even though our electrons move in a circle. Now, how am I going to make sure my electrons move in a circle correctly? You can kind of start anywhere in theory, but I like to start with one jump in particular to make sure I'm doing it correctly. And that is to close this gap. Okay, for a sigmatropic reaction, you can't go wrong if your first step is jumping across that gap. Notice the tail of my arrow is at a pair of electrons, like it always has to be. The head of my arrow is at the atom that's going to be accepting those electrons. And again, because this is a sigmatropic reaction, I can't go wrong if my first step is to close that gap, meaning to jump across what is the gap in my ring. And then from there, I'm going to make sure all my electrons move in a circle. All right, so now the base of my electrons is going to be this pi bond going to this atom. And then this is the really weird one, which is now the base is going to be at a sigma bond and move to this atom. So that's why I like to start with closing that gap, because then I can always correctly predict which sigma bond is going to break. So in theory, doesn't matter where you start. In practice, I like to go 1, 2, 3 with my arrows. It makes it so that I'm always going to get the correct sigma bond that's being broken. Okay, and if you're having trouble following the arrows, sometimes the easiest thing to do is just sort of to start out with your hexagon, and then we can erase bonds that were broken, draw in our double bonds, all that good stuff, right? But we can sort of make sure that we're on the right path by starting out with the same kind of like framework here. Okay. Notice originally this bond wasn't there, but it was formed in my first jump here. Let's say we have 1, 2, 3, 4, 5, 6. What happens to this pair of electrons?
It becomes a double bond between 3 and 4.
Nice, yep. So sort of color coding here. This pair of electrons is from my green jump. What about this third arrow? What does that do?
It breaks the bond.
So I'm gonna have to now erase this bond between 4 and 5.
And those electrons now make a double bond between 5 and 6.
Yep. Boom. Okay, and this is this red pair. I just started out with the hexagon. I knew that I was gonna have to erase a bond, but it's just kind of easier to start out with this shell, and then you can make sure that it matches with your arrows. In my mind, it makes it a little bit easier. If you can get it just from that picture on the left, great, that's fantastic, right? But just kind of trying to break it down into a little bit more simplified steps. I think it makes, in my mind, it's a little bit easier to actually draw the whole structure and then erase. And notice that there's another defining feature of these signal. Let me actually like clean this up without all these markings on it, so maybe it's a little bit clearer. Okay. This was my reactant side. This was my product side. One of the defining features of these sigmatropic reactions are you have these two double bonds that are located 1, 2, 3, 4, 5 carbons away from one another. And they're kinked in such a way that they're in kissing distance. And notice that that's the exact same on both sides. That's the same on my product side as well. You should always have double bonds that are kind of right in kissing distance of one another. Which is not something you hear people say in chemistry a lot, but it's something people say in biochemistry a lot with regard to proteins and such. So yeah, it's a phrase that I use. Anyways, so then the last step in these types of problems is not only going to be to predict the product, but which way does this equilibrium lie towards the reactants or towards the products? What am I looking for?
It's the product side.
It is the product side. What am I looking for that's going to tell me which
Substitution
more
of
substitute.
the alkene.
Same exact thing that we were worried about with that first example problem that we did, going all the way back. Where was it?
Wait, what did they say? I couldn't hear the recording.
It's okay. It's cool. It goes back to this slide right here and the alkene stability. The fact that a more highly substituted alkene is more stable. So what we're going to do is we're going to look at our two products or our two molecules and determine which one is the more highly substituted alkene, which double bond has more substitution.
Products.
So it's the products. So let's just convince ourselves of that real quick. For this one right here, it's 1, 2 substitutions. For this one right here, there's 1, 2 substitutions, and then you got 2 hydrogens on the end. Right? We don't like to draw those in because it gets ugly. Whereas on the product side, I have 1, 2, 3. 1, 2, 3. So in this case, it would favor the products because that is the more highly substituted alkene.
I can't remember from the week 3 challenge problem. Was it the sigmatropic ones that you had to start with a straight chain, do whatever, and then turn it back into a straight chain?
Probably, yeah. I mean, I think on the challenge problem, yes. So
Yeah.
in this one, if you want to, we can work on that now. Kink this one back out into a straight chain. Yeah, I mean, again, if I'm gonna do it, I'm gonna go.
Would we kind of do the reverse thing of see what is trans for each bond and
Yeah, in this example, these bonds don't actually have stereochemistry, but that would be exactly what you would do if it did. And by that, I mean that this substituent and this substituent are, well, no, I lied. They do have stereochemistry. JK, they do. All right, so yeah, we can make sure we got it all the same. 1, 2, 3, 4, 5, 6. Let's just straighten out all those carbons that are in that chain. So 1, 2, 3, 4, 5, 6. Got our double bonds in the right position. And then I'm just going to have to add the other groups in such that my stereochemistry is correct. It's not going to be cis-trans, it's going to be EZ, but nonetheless. So I guess before I even do anything else, I can make sure that carbons 2 and carbon 5 have methyl groups. And now I'm going to have to make sure that these 2 carbons go in there in the correct conformation. In this case, I'm going to make sure that they are both E. Cool.
that's way easier than what I was trying to do of like rotate each bond and then like adjust it, rotate another bond, adjust it.
Yeah, honestly, I'm pretty good at rotating stuff in my head. And when it comes to folding something into a 6-membered ring, still can't do it. I honestly do exactly the procedure that I laid out, where I'm going to just sort of connect things and make sure that my stereochemistry is correct.
Yeah, that's way easier.
Okay, so let's jump actually. The biggest takeaway from chapter 17, especially in terms of the ACS exam, is the aromatic, anti-aromatic, non-aromatic business. Okay, being able to classify a molecule as anti-aromatic, non-aromatic, or aromatic is huge. Yeah, let me go through this one and then we'll do that. Oh yeah, sure. Same sort of deal though, Thea. You're just going to kink it into that ring and make sure that the stereochemistry of that one bond is the same. It's actually was a little bit trickier of a looking of a problem than it was, because that 5-membered ring you can treat as just any other substituent. But we can do that at the end here. I'm going to put some compounds down and I want you to classify them as being aromatic, anti-aromatic, or non-aromatic, okay? and let's focus on these top ones here. These bottom ones with these heteroatoms are a little bit more difficult, so let's just start with the top here. For this first one, what does everybody think? Aromatic, non-aromatic, anti-aromatic, what do we got?
Anti?
I got non. I got non.
Non is correct. So why non?
Because the top is sp3 hybridized.
Boom. So this guy right here messes everything up, this sp3 hybridized carbon, right? In order to be either aromatic or anti-aromatic, you have to have p orbitals sticking up out of that ring, this conjugation network. That guy right there is sp3 hybridized, meaning it doesn't have any p orbitals, so it's going to break any amount of conjugation across that ring. So that would be non-aromatic. So that's what you're looking for non-aromatic compounds is there an sp3, or another simple example would be if it's just not in a ring. Those are all, this is a tri-conjugated or a conjugated triene, but it's not in a ring, so it can't be aromatic. So for the bottom ones now, okay, so this is sp2, 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 and this pair of electrons here is living in a p orbital as well. Is this going to be aromatic, or so we know it's that it's not non-aromatic. Is it anti-aromatic or aromatic? What's the rule that we're looking for there?
Huckle's rule.
Huckle's rule, which is that 4n plus 2, does it have, let's just move all this down. Right, so Huckle, I think he's got a weird accent in there. Anyway, Huckle's rule is that the number of electrons is either 2, 6, 10, 14, 18, 22, etc. It follows this 4n plus 2 pattern. So if I plugged in 0 for n, I would get 2. If I plugged in 1 for n, I would get 6. If I plugged in 2 for n, I would get 10, etc. It's really important for everybody to know that when I say 4n plus 2, I'm not talking about like this math equation that you're trying to solve for. I'm really talking about this series of numbers here.
It is aromatic.
So in this case, it has...
And n was the number of double bonds, right?
No, n is not something that you solve for. You plug in every possible integer for n, and it will give you a series of numbers. So it's not a math equation. It's a shorthand for this infinite series of numbers: 2, 6, 10, 14, 18, 22, 26, 30, 34, 38.
Yeah, I know how series work, but n has, like, it is changing depending on how many double bonds there are in there, right? So if we had 0 double bonds, that would be 2. If we had 1 double bond, we'd be at 6, right?
No, it doesn't really have a correspondence with the number of double bonds, because things can be pair of electrons or empty orbitals. It really doesn't have any connection to number of double bonds. It's just shorthand for a series. If the number of electrons is one of those numbers in the series, it's aromatic. So this would be an example of a compound that's aromatic, that has 2 pairs of pi electrons, and thus 6 total. This has 6 and has 3 pi electrons, or 3 pairs of pi electrons. I don't know if that answers your question.
The Huckle's rule, it can also, well, I think about it as if there's an odd number of pair of electrons, then it's good to go.
You can think about it in terms of total number of electrons or pairs of electrons. Whichever one is, to be honest, the originally stated Huckle's rule is this 4n plus 2 business, so that's how I think about it. But it's absolutely, you could think about it in pairs of electrons, and an odd number of pair of electrons is Huckle's rule as well.
Okay.
Okay, I have a question with that one. So the reason why that one's aromatic is because there's an odd number of pairs of electrons. So that little pair right there would be considered as a pair of electrons?
Yep.
So that's 3, so okay. And it's also because down right there is also an sp2 hybridized?
This lone pair here.
Yeah.
Yes.
Okay.
Which I mean, again, if you watch that other aromatic compounds video, it talks a little bit more about this. But the bottom line is it will make sure to be sp2 hybridized so that it can participate in that aromatic compound.
Okay, yeah.
Okay. Similarly, if we go down here, we have 1, 2, 3, 4 sp2 hybridized, and then we know that carbocations are always sp2 hybridized as well. So this is again got that conjugated network of atoms, so we know it's not non-aromatic, but it only has 2, 4 electrons or an even number of pairs, so this would make it anti-aromatic.
So for example, so if that one had like a third pair of electrons by chance, and I know this one's not possible, but like, is it possible for like so what if it had like 3 pairs of electrons? I had 3 pairs of electrons, and one of them had a positive charge. What would that make it?
So oops. Dang it. Hold on.
I know the quiz there's one like that on, but I don't know.
It's like this.
Yeah,
So,
there you go, like that one.
So you tell me.
Okay. So there's 3 pairs of electrons, and then that one, they're all sp2 hybridized. So would that make it aromatic?
Mm-hmm.
Okay.
Even if one of those double bonds, what if one of those double bonds was gone and it had a pair of electrons on
In place.
Well, you're never going to have a
Okay.
carbocation next to a carbanion.
because then they'll just transfer over.
Yeah, then it'll just form a bond.
Okay, yeah, never mind.
Okay, so now we get to these heteroatoms. And what makes these a little bit more difficult is because now we're talking about this lone pair of electrons that exists on these atoms and whether or not they're going to participate in this resonance in this ring. Okay. In order to participate in resonance, these electrons would have to live in a p orbital. Okay, meaning that the nitrogen itself is sp2 hybridized. Okay. Most of the time we think about pairs of electrons as living in hybrid orbitals. So if we imagine something like ammonia, something we learned about all the way back in Gen Chem, we would think that this pair of electrons lived in an sp3 hybridized orbital. Okay. You know, I don't know, without going too much back into reviewing hybridized orbitals and all that business, the bottom line is if this ring can be aromatic, it'll put those electrons in a p orbital. If it's not going to be aromatic, it won't. Okay, or rather, if it's going to be anti-aromatic, it won't. So what we have to do here is first, in order to determine whether this compound is going to be aromatic or non-aromatic, we have to first convince ourselves that these guys are indeed sp2 hybridized. That's the first important thing. And then we're going to look at this nitrogen in this pair of electrons. It will be sp2 hybridized if it will make the compound aromatic. Okay. In this case, we have 1 pair of electrons, 2, 4. If we include this to be 6 total electrons, does that fit Huckle's rule or not?
Yes.
Yep, so that would fit Huckle's rule. So indeed, this one will be aromatic, and this nitrogen will be sp2 hybridized. This pair of electrons will live in a p orbital.
I know this may sound like a dumb question, but so when you're counting like the hybridization, so so the lone pair, you don't include that on the hybridization, or?
Say it again.
Oh wait, 1, 2.
So the whole point is that that nitrogen is going to change its hybridization so that that pair of electrons can participate in resonance.
Okay.
So it's going to specifically say, I'm going to put this, well, I mean, it's not like it's got a brain, but it's like, I'm going to put this pair of electrons in a p orbital because that will make this compound aromatic.
Okay.
So then let's do another example where it wouldn't do that. Get my 7-membered ring drawings on here. Now we have this, ooh, so close. Now we have this compound here. And again, the question is are these pair of electrons going to want to be participating in that ring or not? I guess first thing we got to make sure is that everything else is indeed sp2 hybridized. Okay. If this pair of electrons was included in the ring, how many pairs of electrons would I have in that ring total?
So the end up being 4, which it would violate on Huckle's rule.
Yes. So if this one was going to participate, that would make it anti-aromatic. So instead, it just doesn't allow them to participate, meaning it doesn't put it in a hybrid orbital or in a p orbital. So in this case, this is an example where this nitrogen would instead be sp3 hybridized, and this pair of electrons would live in an sp3 orbital so that the compound was non-aromatic. Because otherwise, it would become anti-aromatic, and anti-aromatic is bad. Right? If this pair of electrons did participate, that would give me my 8 or my 4 pairs, which isn't good. All right, so this example, yeah, real quick. This example here would kind of like be no different from this one here. We would say that this one's non-aromatic because this atom here is sp3 hybridized. It's the same thing in this heterocyclic compound as well. What's your question?
Okay, so if we're looking at this molecule and that was an oxygen and it had the 2 lone pairs, I guess my question is, will it want to go to the 10 or will it want to stay at the 6? Like, does it matter? Because either way it would be aromatic, right?
I see what you're saying. Both pairs of electrons on oxygen can't be involved in resonance.
Oh, okay. Okay.
Because
So it can
if
only
they
use
were,
one pair.
It can only ever lend one pair because
Okay.
those p orbitals would be perpendicular. They wouldn't be parallel.
Oh, okay. Okay.
So you can only ever have one pair of electrons involved. So let's just do another set of examples here that are similar to kind of hammer this home.
I feel that kind of goes over like the conrotary, disrotary kind of thing, where you have to have all the p orbitals like up in the same direction.
Yeah, I mean, that's the basis of aromaticity and anti-aromaticity period, is you have to have this like ring of p orbitals that can participate in conjugation. All right, so let's do one more example here using these 2 compounds. One of these is aromatic, one of these is non-aromatic. See if you can't tell me which one's which.
What did you say? The ones with the nitrogen, the example with the nitrogen, they were both aromatic or non-aromatic?
No, the first one was aromatic.
Right, but the one with
because
the 1, 2, 3, 4, 5, 6 carbons,
is non-aromatic.
because it has too many
Because so the nitrogen, if this pair of electrons was included, it would be anti-aromatic. So
Right.
instead, it's just not going to include the pair of electrons. It's going to stay sp3 hybridized.
right. Okay.
So it's like no different than this example here, where this carbon atom's sp3 hybridized. So we call it
Exactly.
non-aromatic.
Got you. Thank you.
Yep. All right, so again, this is very similar example here. Here we have 1, 2. So if this pair of electrons was included, that would be 3 pairs or 6 electrons. That's good. That's aromatic. And that would make this oxygen is going to be what hybridization?
sp2.
Yeah. sp2, right? That gives me everything in that ring is sp2. Awesome. If I go over here to this example, I have 2, 4, 6. If I included this one, that would be 8 or 4 pairs. That's bad. So that would mean that this oxygen is going to be what hybridization?
sp3.
sp3. Right? So notice it'll change its hybridization in order to be aromatic. It's not going to change its hybridization to be anti-aromatic. So in this case, this one is non-aromatic. And then the last sort of annoying thing that I can ask you about this is for each one of these, tell me the number of delocalized lone pair electrons and the number of localized lone pair electrons. Okay, so first of all, when it comes to oxygen, just like, is it Yesenia? Is that how I say it?
Yesenia.
Yesenia, cool. Just like Yesenia brought up a good point, which is with oxygen, it's got these 2 lone pairs of electrons, right? Important to remember, one of them is always going to be localized. They can't both be participating in resonance. So right off the bat, we can just pick one of, on each of these oxygens, pick one pair and say that it's definitely going to be localized. Both of them cannot be participating at the same time. So yeah, so you can start out with that right off the bat. The question is, what about the other pair, right? It's going to be delocalized if it's aromatic, and it's going to be localized if it's non-aromatic. So in this case here, this pair of electrons was participating in that ring, right? That's why it's sp2 hybridized. So I'll have 2 lone electrons, 2 electrons that are delocalized, and 2 electrons that are localized. Over here, none of these electrons are going to be delocalized. If they were, that would make it anti-aromatic, which is bad. So instead, all 4 of them are going to be localized.
Could you scoot it to the side so we can see what was okay. Is that how you're going to word it on the exam? if it's asked, because I was kind of thrown because you said lone pair electrons, so I thought you
too.
meant the pairs of, not
Then I
the
would have asked
number
for the
of.
number of lone pairs, not lone pair electrons.
Okay, so if the S is on the pairs, then we're going for pairs. If the S is on the electrons, electrons.
Yes.
Right. Okay.
I would just say number of lone pairs or number of lone pair electrons.
Okay.
Can you explain that one more time real quick? Sorry.
Sure, which, yeah, okay. So here, I've colored all the delocalized electrons in this dark blue. And you see that the oxygen, this pair right here, is going to be delocalized because that's what brings me up to 6. You like the pairs, right? So 3 pairs, that odd number, which is aromatic. And then the other pair in cyan is the 2 that aren't going to participate in resonance.
So when you're saying pairs, you mean like each electron?
Well, no, so there are 6 electrons or 3 pairs of electrons.
Right. So for you, when you say the number of delocalized lone pair electrons for this,
I'm referring to these 2 right here.
okay.
There's 1 lone pair and 2 lone pair electrons that are delocalized. You're saying one and the same thing. It's,
Yeah, I just gotta.
yeah, it's the same question that Dylan had. It's kind of a, whatever, a nuance. Do you refer to the total number of electrons or the number of pair of electrons? It's kind of what you kind of got to keep straight language-wise. And then for the non-aromatic compound, all 4 of those electrons on the oxygen would be localized. Otherwise, it would make it anti-aromatic.
Oh, we're referring to the electrons alone that are not double bonded.
Right, because those are not lone pair electrons, they're pi electrons.
Wow. Okay, I got it. Sorry.
I see where you're getting at, yeah. Yeah, the lone pairs are on the heteroatoms. All right, so obviously we have the exam on Thursday. I do have office hours for 3 whole hours on tomorrow. So if you guys want to come to office hours and go through practice problems or whatever, that's cool. We can absolutely do that. I highly recommend you guys come to office hours. It's basically this exact same format, usually not quite as many people. And yeah, we could just do practice problems the whole time if that's going to be helpful.
One quick question about tomorrow. If we need, could you go a little longer? Because I'm in class until like your last hour-ish of what you have scheduled.
Yeah, that's fine.
Okay.
Professor Chrysippus?
Yeah.
Well, would it be possible to review Birch reductions real quickly when there are multiple substituents?
Oh, we're not going to worry about when there are multiple substituents.
Okay, so just single substituents then.
Yeah, the only thing you really have to know is the difference between the electron withdrawing groups and the electron donating groups and how that will affect the regioselectivity of the product.
Okay, thank you.
Yep. Cool. If you guys don't have any more questions, I'm done with all the practice problems that I dug up here. I'm happy to stay and answer any specific questions that you guys have though. if you want to see a problem done or something like that.
Thank you, Dr. Corsapius.
Yeah, absolutely. Have a good one.
Have a good day, Dr. Corsapius.
Yep. Bye, guys. And if you want to hang around, we can do the practice exam as well. Otherwise, you can always do it tomorrow at noon.
No, I can do it now.
Okay. All right. I'm going to stop this recording because that doesn't need to happen.